So, hello everyone, I'm Ssu-Ting Lai. You probably know me because I'm a helper in a SPIN workshop, but actually I'm nothing connected to the SPIN project. And so I'm a bit shocked when I look at my name on a list. Oh, I'm gonna give a lightning talk. But okay, so this is my title for my PhD thesis, and these are the people I'm working with during my PhD. So I'm from IPGP, and hopefully I can find some connection with SPIN. So usually I show this first. This is a common conceptual diagram you can find in the textbook to show the concept how the earthquake happens, especially for tectonics, how the plates dislocate with each other. But actually, when the faulting process is much more complicated than this. So there comes another conceptual diagram. So when a stress or a pressure applied to an environment, actually there are some micro faults, relatively small things. Crack happens inside the materials, and more when the stress becomes higher and higher, and can kind of form in the similar directions. And when it passes on thresholds, they all connect together, the fault forms. Earthquake happens. So this kind of situation can be more easily seen in a lab experiment in a small scale. So for example, in their work, they separated what they observed in the lab into 4 steps. So in the very first part, when there is no stress apply on the rock, there are a lot of pre-existing pores and cracks. And when you apply more and more stress, and then the microcracks will be enclosed. Then when the stress becomes higher and higher, pressure becomes higher and higher, there are microcracks forming in the site like this, and kind of follow the same direction because of the direction of the principal stress. And then at the end, it cracks like this. So because we can observe it rather easily in the lab, so then we are thinking about, we want to answer how this earthquake happens, and more further saying that what happened before the earthquake rupture. And as a seismology, we want to see what kind of feature can we detect by sending seismic waves. So in my PhD thesis, we want to combine the laboratory experiments and numerical modeling using the SEM3D software, using a full waveform to map weakening process and also study time-lapse structure changes during rock deformation. We expect to bring something we observe in a small scale to answer some big question in big scale to know earthquake nucleation process. So this is what I did. So this is me who is doing experiments in Japan. So I did triaxial deformation experiments on granite rock. So I crushed the rock. And this is what we have, the data we have. So I placed one source one receiver at one side of the rock and recorded at the other side of the rock. So it's like at every stress compression stage, we send one signal from one side and record it at the other side. And it shows like this. So this is displacement. It's actually also can be understood as deformation. So when the displacement goes high, we have a strong deformation. And you can see that when the deformation goes really, really high, the first arrival become earlier and then become later. And also you can see that amplitude become really, really small when almost close to the failure. So we want to understand all these waveforms and understand what's happening here at the very last stage. So then I start to test a lot of trial and error on numerical modeling to test on different geometry and find the best model, the granite rock inside and with the additional layer outside using the silicon glue jacketing parameters. And actually it acts at a partial absorbing, partial reflecting boundary condition and let my synthetic match better with my data. And after I find the best model, then I go for Monte Carlo waveform matching. It's like I progress a lot of elastic and elastic models, like actually over 6,000, considering VPVS, P and S wave velocity, QPQS, P and S wave attenuation all together, and do the grid search to find the best fit models by fitting my synthetics with the data. So because we have this kind of good search, so I can easily remove the outlier and find the best evolution of the parameters during the along the differential stress. So this is my best fit waveforms. The red is the data, and the black are the synthetics. So you can again see the first arrival going like this. You can see the trend. And I also plot the evolution of velocity like this. So it's related to the figure I mentioned before, the 4-stage. The first velocity will go high a little bit and then drop really quickly when the micro cracks happens in the material. And then I also plot the attenuation, the quality factor changes, and 1 over Q, which is mean the higher the 1 over Q, the higher the attenuation. And by simultaneously inverting VP, VS, QP, QS together, so we can obtain the attenuation change in terms of quality factor easily, that we don't have to use the relative amplitude calculation anymore. And we found that using this kind of method, the elastic and elastic structure changes during rock deformation can be obtained, and attenuation could be the key to monitor the stress condition. But after doing this kind of 1D search, we want to go for 3D. So then I do some one-station seismology on rock using this kind of simple, again, the one source, one receiver setting on metals and rocks. So I study the wave propagation in sample using seismograms, snapshots, and also kernels. But when I go for rocks, I need to add some random heterogeneous model. So I, again, produce a lot of models with different grain size and match it better, the synthetics with the data, and found that waveform can tell us the wavelength of the heterogeneity, which is really good. We can apply in many places after. So thank you. This is what I did 2 years ago in Jundupila, so I'm nice to come here again. Thank you.